May I have your attention, please? If you gradually work your way to your seats, we can start. Unless you want to stay here all night. It's 6 o'clock and we can go ahead and start. Okay, so I have the pleasure of chairing the second session in the hardware tonight, and I would like to introduce our next speaker, who is Dr. Amir Khosrowshahi, who is the CTO of the AI product groups at Intel and also a vice president at Intel. Amir was the co-founder and the CTO of the startup company called Nervana that Intel acquired, and he's carrying his journey now at Intel. So let me tell you a little bit brief background about Amir, and then you know that why you're so lucky to have him tonight here. Amir has studied mathematics and physics at Harvard and got his master's again at Harvard in physics, and goes to UC Berkeley to study computational neuroscience. So if you remember, the paper that Professor Yang Rabai was quoting earlier, if you remember, was published in PLOS by a neuroscientist. Could a neuroscientist understand a microprocessor? I think that this man is the best man to answer that question. So without any further ado, Amir, please, stage is yours.
Thank you. It's a quick one. So good evening. Thank you for inviting me. What you didn't mention was after studying physics at Harvard, the only employment you can get as a physicist is to work on Wall Street. So I actually worked on Wall Street for quite a while. It was actually pretty fun. And you didn't mention also that after that, I spent 6 years of doing nothing, not working at all, traveling, and I got really interested in ski mountaineering. But it's not relevant to this talk. So I perhaps need some career coaching or advice. So the talk is, it's great to have Jan. Jan was actually an advisor to my startup, Nervana. And the previous two speakers, they make it a lot easier for me to present. So some of the slides I'll go through quite rapidly. Don't be alarmed. But my talk is about how to build an artificial intelligence platform. What does that even mean? What does it entail? What are the difficulties? What's the silicon component? What's the software component? And as Ali mentioned, I was at a startup, Nervana, and my background is as a neuroscientist. And it's kind of an odd state of affairs for someone like myself to be leading an effort like this at the iconic chip manufacturer. I don't even like computers. Sitting at your desk doing this thing is a very unnatural thing for me. But I guess this is, again, the state of the world. You have neuroscientists, mathematicians, hardware experts, all working together to advance technology. So the main theme, though, of my talk is this very basic thing that's happening in computation today. Computers have been used for all sorts of wonderful things in the past 10, 20, 50 years. And the nature of things that we're doing today are quite different than they were just 10, 20 years ago. When I was working on Wall Street, most of the computation on finance and also most of the compute in the world was used to run linear programs. Today, most of the compute, or it's starting to be so, that most of the compute is being used to process large amounts of data to train statistical models, like deep learning models or graphical models, and to perform inferences on this data. So this is a very major trend of our time that just bears stating. And silicon, software, systems, solutions are all starting to, the changes that are happening at each of these levels is reflective of this fundamental change. So I will give you a slightly rotated version of Jan's presentation introduction in the space of introductions. So the history of AI to me started in the late 1930s with individuals like Alan Turing and Kurt Gödel and others defining the notion of computability. What can you compute? What are the limits to propositional logic? What's the notion of universal computation? What does that mean? And then in the early 1940s, some of the same individuals started building the first computers, the first stored program computer. John von Neumann is depicted on the left, on the right, above. And one of the first on the left. Okay, I got confused there. John von Neumann, standing next to the EDVAC, one of the first stored program computers. Very successful architecture. We still call it the von Neumann architecture. It works. General purpose computing alongside a large set of software. You can solve a lot of problems. And if you look at the first proposal John von Neumann wrote, he had the problems listed that he wanted to solve, and the architecture was motivated by just a set of problems. Ordinary differential equations, different kinds of partial differential equations, other kinds of things he wanted to solve. It was wartime. They were building nuclear weapons and so forth. So after this remarkable period of building the first computers, in the late 1950s, near the end of his life, John von Neumann was preparing a lecture series for something he was going to present at Yale. Unfortunately, he passed away before doing so. And this book called Computer and the Brain was published posthumously. And here is where he started looking at some early results that were coming out of the field of neuroscience. Things like Hodgkin-Huxley equation, how signals propagate along axons of neurons, what the microarchitecture of mammalian cortex looks like. You have these neurons that have elaborate dendritic arborizations. They're synaptically coupled to lots of neurons in the vicinity of each other, as well as having long-range projections. How do we look at how the brain operates? And the architecture and some of the early efforts by McCulloch and Pitts and others to have simplistic models of neurons, how do we borrow from this knowledge and inform the next generation of computers that we'll be building? So my view of my work at Intel today is kind of scratching at the surface of some of these ideas that he had presented in 1957. And actually, Jan touched upon some of them already. How do you build a system where memory and compute are intermeshed, they're closer together? How do you build a system where you can do exact computation with inexact elements? These ideas were already there in John von Neumann's book. So now progressing forward to today and the state of affairs today. So I am a neuroscientist, and I am still a novice at silicon. And what I mean about the limits of computation, I don't mean it just about the silicon, but about the whole stack, all the way up to the algorithms and NP hardness and so forth. But one of the things I keep hearing is that there's the end of Dennard scaling, there's the end of this other law, and we have this explosion in data that we have that will require lots of compute. And I feel like I came late to the party, that we have all this data now that needs a lot of compute, but people like Jan and others are telling me we're done, we can't progress any further. So I took somewhat of a hard look at this as a novice, and here is a paper by Igor Markov in 2014, August 2014, a review paper in Nature that I read and then I followed up on, looking at the limits of computation at all these different levels, at the silicon level, at the EDA tools level, what do you get algorithmically by stacking, heterogeneously, homogeneously. And if you look at them carefully, the limits are quite loose, that there's still a lot of room left at the bottom, as Richard Feynman said, in each of these areas. And many of you know this, I'll just repeat it, that you have, for example, you're shrinking transistors to 10 nanometers, but you're not just shrinking them. You're introducing fins, you're wrapping dielectrics around these fins, you're making the fins taller. You're not just making things smaller. The single atom thickness of the high K dielectric is not really a limit. And there's so much evidence for this happening over and over again. The laser that you use to etch silicon is 193 nanometers. It's an argon fluoride laser. There's an Abbe diffraction limit. There's a natural limit to optics, and that gets you down to 65 nanometers. How are we etching things in 10 nanometers? Because there's a lot of things you can do to get down to 10 nanometers. There's computational lithography and so forth and so on. And across all these areas, in terms of the network bottleneck on the chip, you can have multiple metal layers, as well as in the space of algorithms. There's new algorithms for doing place and route using different kinds of relaxations of NP-hard problems, convex relaxations. I feel like there's a lot of room for innovation across the stack. So I'm looking forward to working at Intel, all the newfangled kinds of things like silicon photonics and memory technology and bringing them into my field. Okay, so going back to neuroscience, my field was vision, visual neuroscience. So half of it was doing experimental neuroscience, and half of it was doing computational stuff, machine learning, computational neuroscience, computer vision, distributed computing. So the problem that I was trying to solve for my PhD was to understand the mammalian cortex, a small piece of it. And in mammalian cortex, what I'm referring to is the 1 millimeter layer at the top, most of the squishy thing that's in your skull, the gray matter that Jan referred to. And it's fairly intractable. Unlike the cerebellum that had this regular structure that looks like an associative memory, the cortex is quite different. It has 6 layers. There are distributions of cell types. They're synaptically coupled in certain ways. There is evidence that there is a microarchitecture that's repeated across cortex, but it varies according to function. What I was trying to do is stick needles into this tissue vertically using silicon probes and record and try to figure out what it's doing. What are the elemental computations it's performing? How does it map to cool things that were going on in machine learning at Berkeley, where I was studying all sorts of cool stuff, interior point methods, conic optimization, graphical models, other forms of machine learning. Is there a mapping? Is there a correspondence? So this problem turned out to be really hard, and I'm not sure if I made any progress at all, but it's still my passion. And for our startup that we started in February 2014, we tried to do the reverse problem, an easier problem. Just then, Google's and Facebook's were using deep neural nets to create products, solve machine learning problems, achieving state-of-the-art in many domains. So we saw neural networks, fairly simple set of primitives, very simple algorithms, easily trainable. We felt like we could build a substrate, workload-optimized hardware, silicon, ASICs, for deep learning specifically, along with building a stack on top of the silicon to get to 10, 100x improvement in performance that creates an enabling technology. So that's what we did at the startup. And now we're at a very good state. I am a neuroscientist. I'm learning from people who do silicon at Intel, and I'm learning quite a lot. And there's a good give and take between people like me and people like Jan, and it occurs at all the different levels, not just at the silicon level, but at the algorithmic level. And ideas from cognitive neuroscience are coming into designing systems, large-scale systems. How do you build a reinforcement learning system that's robust and scalable and has assurances of correctness and so forth? There's a good interplay between the two. Actually, there's not much information flowing back into neuroscience yet, but hopefully there will be more in the future. And I have some idiosyncratic history. The history of me going into silicon I think is interesting, and I think it's important to me and our effort at Intel. And my initial inspiration was I took the laboratory electronics course at Harvard by Paul Horowitz. Paul Horowitz wrote this book, Art of Electronics. I'm sure many of you are familiar with it. It's a wonder of nature. And Paul would, so I was actually the worst student in his laboratory electronics class. I studied theoretical physics, and it was a real struggle for me. But what I learned from his class, he would spend one lecture in every class he taught, physics class, atomic physics, or whatever, on the SETI program. He's very passionate about this grand challenge for civilization to find evidence of extraterrestrial life. And as part of his effort, his work, he would build these incredible machines to address some problems that he faced. So here's depicted next to one of his second or third generation machines. It's called the Beta. I think it's a 1 billion element extraterrestrial assay. It's a giant Fourier transform engine that is able to process. You have the full spectrum of frequencies, and you want to do analysis of very narrow band signals. And he built this thing from scratch, hand soldered the memories, used all the tricks in his book to get this thing to work because he wanted to solve this problem. And that was very inspiring me to see this, and it's kind of stuck in my head that in order to really solve a novel problem, you kind of have to get pretty crazy. The second source of inspiration was more recent. It was in around 2008, 2009, was from this effort called the Anton, and it was started by David Shaw, who is a famous hedge fund manager. D. Shaw is a giant hedge fund in New York, and where some of my friends work. And the purpose of this supercomputer was they wanted to be able to do biomolecular simulation at a much finer timescale, at the femtosecond timescale. And in order to do that, they decided to build everything from scratch. So they built the silicon, which is on the right. It's a processor, has lots of compute, has lots of I/O with neighboring chips. You can connect them in a mesh, a toroidal mesh. The 3D toroidal mesh is because of the 3D geometry of the liquid they're trying to simulate. And they produced results like the following. This is a potassium channel, and it's relevant to this talk because the potassium channel is essentially a transistor for your brain. It allows potassium ions to come in and out of a neuron, and it causes the neuron to generate action potentials from changes in membrane voltage. And you see those gyrations of the arms of the protein, this complex protein. Those have manifestations and properties of the neuron, of the system. So, and there's a number of science and nature publications, a remarkable number of them, that were generated from being able to simulate things at this very fine time scale. If you simulate it at a much coarser time scale, you don't see these things happening. So pretty remarkable innovation that was driven by building, again, something from scratch. And we borrowed a lot of things from the Anton project in spirit, and actually we stole one of their main people, Ron Dror, is a professor at Stanford, to advise us. So now stepping back to the real world, why is this, what do I do? What's relevant to Intel? Intel is a business, and it has everyone as their customer, the whole world. A lot of the compute in the world runs on Intel processors, and this is what I spend a lot of my time in, is traversing up and down the stack of hardware to working with customers of Intel. So just quickly going through this space of applications, the industry, and how it's being transformed by artificial intelligence and neural networks and machine learning. It's quite surprising to me because I started in this field in 2006, and for me it's just been a really slow progression until today. I was in a lab where Jeff Hinton and Andrew Ng and Jan LeCun and all these luminaries of the field would hang out and complain to each other how their papers weren't getting accepted into NIPS and nobody cared about them. And all of a sudden they became pretty famous. This is quite remarkable. But for me, it was more of a gradual progression, and the adoption in industry has been also gradual, but it's been really marked, and there's material things happening. It's not hype. You hear in the press all the time, AI this and that, but some of the things, some of the applications, maybe they're already good enough that you're taking them for granted. So in the consumer space, those are the lowest hanging fruit, where there are real use cases for doing things like categorizing whether or not an image has cats and dogs can result in ad revenue. So you see very rapid adoption there. You have speech systems, speech recognition systems, simple natural language understanding systems like smart assistants like Amazon Echo, which I think is a fairly successful application of neural networks and AI. In the healthcare space, there's really material things happening in diagnosing illnesses early and helping patients. I studied the visual system in the eye. There's one particular application where you can take an image of the fundus, the back of your eye, the retina, and the eye is very metabolically active. There's a choreo capillaris that innervates the back of the eye, and if you take a picture of someone who's sleeping in the dark, you'll see these two big blobs because they're always active. And because they're very metabolically active, if there's something weird going on in your body, like you're getting diabetes, it turns out that there are manifestations in your retina. So people knew this, and now there are methods to do a simple convolutional neural net to diagnose diabetic retinopathy by taking images and doing straightforward computer vision application. This is a material advance that helps people. In the finance space, I work with exchanges, with banks, with insurance companies. This was my field a while back. The problems they're trying to solve are things like creating autonomous agents to do trading for you, to do optimal trade execution, to do automated market making, to understand the limit order book, the microstructure of the limit order book, and so forth and so on. Just wanted to spend a little time on connecting with reality. So what is AI today? I've shown a circle where I think where we are today. Today, it's mostly deep learning neural networks, as well as some elements borrowed from other kinds of machine learning and other things in the AI space. The space of AI is actually enormous, and it's been slightly steamrolled by deep learning, but this is the current state of things, and I would say that it's highly unsatisfactory. There are many things about deep learning that will change in the near term, and in the long term, things will keep evolving, and you should look forward to it. And if you look 10 years back to a standard textbook in artificial intelligence, like Peter Norvig and Stuart Russell have this pretty amazing textbook on AI. If you look at the distribution of contents in that book, and if you look at what we're doing in AI today, there's almost no overlap. So things have changed in the last 10 years. Just be prepared that things are going to change in the future. So now getting to deep learning, we're building a deep learning processor. We have built one. We're working on the subsequent iterations. So I'll just go quickly through some of the background and engineering involved. So one of the differences between deep learning and classical machine learning, I didn't hear it mentioned early on, so I'll just go through it. It's very simple. So in classical ML, and this is kind of a naive description of it, you take high-dimensional spaces, like spaces of all faces, a picture of someone, n-by-n pixel image. It's quite high-dimensional. And you know that in a face, there are eyes, noses, and other kinds of regular statistical structures. You can actually do feature engineering and map this n-by-n, n-squared space down to k, where k is much smaller than n-squared set of features, and you can stick it into a classifier, train it, and get results. That's how machine learning was typically done before this latest craze, since 2012. Deep learning is different in that the models have a huge degree of representational power. They have lots of weights. They can be trained in a very simple way, and they can learn the statistics of the image, the high-dimensional manifold of images of faces by themselves. And this machine at the bottom center, this convolutional neural net, it's a fairly simple repeated structure that you can train with simple calculus, linear algebra, and stochastic gradient descent, a very haphazard, inefficient way of traversing the space of weights, but it works remarkably well. So that's the main difference today. Some other items that are noteworthy about deep learning. So again, it learns the features from the data. It's able to, they're stacked in layers, and there is some idea of compositionality where the layers reflect learning higher order statistics, or more abstract levels of the statistics of the underlying data. What's nice about deep learning is that the more data you have, the more it improves, the performance improves. So we have lots of data again. We have this data explosion. And the most important thing, I feel, is just the representational capacity of these models. Again, they have lots of weights. They can be trained. The weights can be trained. And you can solve very non-trivial tasks like recognizing 1 out of 10,000 objects in an image, or allowing you to drive your car in the noisy, messy world we live in. And I actually took this slide from an earlier slide because I liked it so much. It's a slide from Jeff Dean, which really succinctly states what's been happening. And I don't agree with the far right necessarily, but again, there's a whole set of machine learning models and algorithms and AI models, and those are the other approaches. And what's happened is that neural networks have really dramatically outperformed these models recently because they can exploit the size of data and the size of the models. And this trend, who knows, is it going to continue? Perhaps. But this has been the state of affairs for the last couple of years. And just quickly, again, so why is deep learning relevant? It's the performance of the models. You have models now in image recognition and speech, which are one of the two top applications of deep learning, where the performance is now better than humans, albeit at some potentially artificial tasks, like recognizing 1 out of 1,000 objects is the one that's depicted on the left. Of those 1,000 objects, there's 20 different kinds of spiders and hundreds of different kinds of dogs. I only know one kind of spider, so it's potentially artificial. But this is a really marked improvement in the last 5-10 years. And okay, so we're at Intel, and how do I think about what our group is doing, Artificial Intelligence Products Group? It's a vertical business unit at Intel, which is an odd thing to have at this iconic chip manufacturer, an artificial intelligence business unit. But this is the kind of the core of the idea that we want to make deep learning a core technology for whatever customer Intel has, whether it's a large enterprise, a cloud service provider, an academic institution. We want it to be like a database or some other technology that you assume you have, and it's generic, that it's at the core of your engineering, and it subserves many different functions. And we borrowed it from Google Brain, which is this really cool entity at Google where you have engineers, software engineers, machine learning experts, now hardware experts, system engineers that build a deep learning infrastructure for the various services at Google. We're taking this idea and we're taking it to all of Intel's customers. So now I'm going to go into a little bit more of the engineering. I'll talk about hardware, software, and cloud platform. And I want to just set the setting and how I think about it. There is a cognitive psychologist and neuroscientist, David Marr, who in the 1970s thought about how information processing systems work, what are the core elements that make systems successful. And he kind of enumerated them into 3 different levels, from abstract to more concrete, and I've listed them here. There's a computational level, algorithmic, and implementation level. The computational level is, what does the system want to do? What problem does it want to solve? Why does it want to solve it? If you're an organism, what are you trying to do to survive? If you're Intel's customer, what do you want to do with your business? What does your user want to see? And what's success? And then at the algorithmic level, it's literally like, what kind of algorithms are you using to solve the problem? What are the strategies? How do you optimize? What objective do you want to optimize? That's a reflection of what the goal of the system is. And of course, Intel makes processors. It's very good at the implementation level. What's the physical substrate you want to use? How do you architect it? How do you scale it? How do you make it power efficient? And so forth. So starting with the hardware, so we optimize everywhere. We have to optimize, just as the Anton project did. We need to make everything faster, because that's how you get to an enabling technology. Just having more multipliers on a chip doesn't buy you very much, because maybe you'll be memory limited, your system architecture will break down, maybe memory is more important than compute. We have to think about all these things in an organic whole. So we built a processor for deep learning, and it's called the NNP. It's a neural network processor, Intel Nervana neural network processor. Impossible to remember even by me. But we just released it, we announced it 2 weeks ago, or 3 weeks ago. And how do you go about building a processor for deep learning? How do you go about building a processor for any kind of computational workflow or machine learning? This is how we went about it, and potentially it's a good recipe for other efforts. If you look at the space of high-performance computing, supercomputers, there's thousands of scientists working on these systems, and they're trying to solve a whole host of problems. So the researchers in this space did us a favor and enumerated all the motifs that appear consistently across these various workflows. So you've seen them listed here. It's a paper from Berkeley, and the motifs include dense linear algebra, spectral methods, sparse linear algebra, Fourier methods, Winograd was mentioned earlier, Monte Carlo sampling, dynamic programming, finite state machines, and so forth. So these are kind of all the things you can do. So deep learning occupies a small portion of these various primitives. A lot of it is dense linear algebra, but there's pockets of deep learning that borrow from these other motifs, like Fourier transforms and Winograd or spectral methods. Sparse linear algebra is important in language models where the input layers are very sparse. They're 1 out of 20,000 words or 100,000 words. And when you're designing your system, you have to decide what are you going to bake into silicon, what are you going to implement in software. And what's kind of interesting about this deep learning and artificial intelligence space is that a lot of these motifs can be actually implemented in neural architectures. So if you've all heard about AlphaGo, the Go game-playing engine, it's a reinforcement learning system. There's a dynamic programming element, and that dynamic programming element is greatly assisted by a neural network architecture for doing dynamic programming. as well as Monte Carlo tree search is another one of these primitives that's kind of outside the space of deep learning. So Monte Carlo tree search and dynamic programming, leveraging neural networks is what AlphaGo is. So borrowing from low-level primitives, dense linear algebra, and as well as high-level ideas like Hamilton, Jacobi, Bellman, and dynamic programming. So we're building a deep learning processor. So what are some of the architectural guidelines? What's important for when you're building yours at home? What do you need to know? So compute obviously is very important. Highly parallel compute is the name of the game. Deep learning is at the very core, the elemental operations are multiply, add, and lookup. So if you can do a lot of those and you can route them efficiently and you can maximize your processor's multiplies, adds, and lookups, you're going to potentially win. Other odd things about deep learning, when we were building our processor, we basically threw out everything we knew about CPUs and GPUs and we started from scratch. Other things that are kind of odd are that you know all the operations beforehand. There's not so much branching. The memory accesses are coherent. They're not random. And the operations are very highly prescribed. You know what's going to happen for the next many instructions. As well as the set of primitives are quite small. We saw the list of primitives. The ones that you want to bake into silicon are actually mostly dense linear algebra and some other operations that are compounded with dense linear algebra, like nonlinearities and random sampling. And this is the product that we released. I mentioned it, the NNP. It's the Intel Nervana Lake Crest. And this is my simplistic, I'm not a hardware person. This diagram has embarrassed my team many, many times. This is not I don't know PowerPoint either. But this is my drawing of our chip. So what is this thing? So it has a lot of compute density, lots of multipliers. A GPU has a lot of compute. It's very successful at this problem class, but our processor has on the order of 5 to 10 times the number of multipliers. If we do a good job, then we should be able to outperform the GPU, which is a more general purpose architecture, noted. The instruction set for the processor is a tensor instruction set, so it's not operating on 32-bit words. It's operating on matrices. So multiply matrix A with matrix B, do a nonlinearity, do a random sampling. Those are single instructions in this instruction set. The processor is designed from scratch, like the Anton, to work in concert with other processors in a mesh. And the mesh topologies can be determined flexibly depending on your workload. So if it's speech, potentially it's linear or it's a ring. If it's images or volumetric data from MRI images, it's 3D. It is very flexible in that sense. And so some of the other aspects of it, there is some element of innovation in the hardware side. It's using stacked memory. The latest GPUs also do use HBM2. And this is a really critical piece of the design because if we just jam in a lot of compute into the chip and use the last generation of memory technology, we would just be memory bound. And you see this in the TPU. The TPU from Google is memory bound because it uses DDR3. But this memory is an enabling technology that was critical for getting high performance. This is a physical manifestation in your data center in a rack. This is what it looks like. So you see those ends. That's the new processor. The blue links are the SerDes interconnects. And what's interesting about the interconnects between our processors is that memory is passed from SRAM on one chip directly to an SRAM on another chip. It doesn't have to traverse a memory hierarchy like in a GPU with NVLink or CPUs using InfiniBand or whatever technology. It's really communicating at the lowest level. The tiles of this processor are matrix multiply engines that can communicate across processors by sending matrices across these SerDes links. So much of the action happens in the space of these blue lines and ends. And of course, you have a host CPU and you have other kinds of technology, 10 gig Ethernet, 100 gig Ethernet, SSDs, and so forth. How do you program this device? So on the right, I don't know why it's so hard for me. It's on the right there, it's on the right here. I'll remember that. On the right, those are the tiles on the chip. And again, they're matrix multiply little cores, and they can communicate using MPI-like primitives. So I am a tile, I pass a piece of a matrix on to someone nearby or to another chip. And I can also do things like I can wait, make the whole system wait. I can do reduction operations on a single chip and multiple chips fairly easily. These are instructions in our systems software layer. There are no caches. All the instructions are fed to the tiles. So it's a general purpose distributed linear algebra processor. That even makes sense. So I would love to see people, academics, take this technology and use it for other things. It is a tensor linear algebra processor. You can do lots of things with it beyond deep learning. However, this iteration is very optimized for deep learning. Okay, I talked about the hardware, and I'll skip to the software next. So what are we trying to compute with these deep learning models? The deep learning models are all data flow graphs. You hear about TensorFlow, PyTorch, Caffe. There's a whole ecosystem for deep learning frameworks. And it's great to have all this diversity. And at Intel, we're kind of the demilitarized zone, as well as NVIDIA, where we support all these frameworks and because people want to use them, and it's great. So the problem that we have, though, is that these frameworks are all essentially doing the same kinds of computations at a certain level. They're performing operations on data flow graphs. So we have this many-to-many problem going from the frameworks, from the users to the frameworks, to the various kinds of hardware that we support and that exists outside of Intel. So first, what is a data flow graph? It's a pretty old idea, and it's actually a simplistic version of an idea that's been around for a while. In the 70s, people were doing automatic differentiation on arbitrary Fortran programs. This is quite a simple set of things, and what's depicted are, in the different colors, there's the orange are the weights of the neural network model or machine learning model. X is input, and the blue ellipses are operations. So you have edges are tensors, and the ellipses are operations. These are the computations you're doing when you're doing deep learning. And why do you want to, what does this bring you? If you build a software layer to do efficient optimization and computation on data flow graphs, what does it bring you? You can basically solve this many-to-many problem. You can take all the frameworks and map them down to a single graph layer, and then you can map it back out to all the hardware. And some of the things that sound perfunctory are really critical for the performance of these systems. They're as simple things as allocating and deallocating tensors efficiently. These tensors can be huge. They could exist on multiple processors at the same time because of their size. There are optimizations you can do for training and inference, as well as other workflows like reinforcement learning, online learning, transfer learning. There's a problem of you have a data flow graph where you need to distribute it across a bunch of processors. Maybe it's a heterogeneous set of processors. That's actually a really difficult problem that we're trying to solve, as well as other problems such as compounding of operations that occur frequently in sequence in deep learning, as well as mapping from one set of frameworks and one set of models from TensorFlow to PyTorch to MXNet. I think I'll skip this slide because I didn't really figure out how to depict it properly. But the state of affairs in the space of data flow graph libraries is quite difficult. There's lots of things going on at the same time. Just be aware that this is something that people are working on. It's very interesting for us. We have our own effort at Intel called Nervana Graph, and we're working with all the various efforts at Facebook, Microsoft, Amazon, and so forth, academia. Now, going to the topmost layer of the stack that you need to do artificial intelligence. My title of my talk is How Do You Build an Artificial Intelligence Platform? The topmost layer is the platform layer. So what is this thing? What are the minimal things that you have to have in your engineering to provide an ecosystem for your data scientists and your other engineers to build these systems? There's the data. You have to have a data set. It has to be curated. It has to be potentially labeled. It has to be potentially labeled for the specific task at interest and the problem you're trying to solve. This is an enormous engineering task, potentially even more complicated than deep learning. You have to have an environment for training models, building models, experimenting, doing exploratory data science, doing hyperparameter searches. You have to have an infrastructure to train the models. And in the previous two talks, you heard that the computational requirements for these models is enormous. Every piece of data has to be touched with a multiply and add many, many times to gather knowledge from this data. So the computational requirements are massive. So you basically need a supercomputer to train many of these models. So the infrastructure has to be there for that, as well as deploying the models so that you can do things like use your phone for speech recognition or recognize things in faces in an image and so forth and so on. The deployment side has very different engineering requirements than the training side, the building the model side, and import. Lots of engineering that is not AI or ML. And this is best depicted in this diagram in this paper that was written by a team at Google in 2014. They were building machine learning systems, and they were confronted with this very non-intuitive result that most of the difficulty, engineering difficulty in building a machine learning platform is other things than the machine learning. So the machine learning is actually that tiny little black square in the middle. And then what surrounds it is all the other stuff. And the other stuff is, you have these Donald Knuth textbooks. It's all that weird stuff that's in those books. Very difficult column store databases, communicating efficiently, lots of heuristics to solve kind of combinatorially difficult problems. It's all in there. So all of that stuff is needed, and there's a lot of von Neumann compute going on in that space. This is the most common thing that people who are new entrants to this space get tripped up on. You buy a box with some compute, you download TensorFlow, you have a data set, you basically don't get anywhere after that. There's always a disappointment. I hear it. It's like, oh, well, I just couldn't solve my problem. It's like, well, it's maybe a little bit more complicated than that. So I spend a lot of my time helping companies with this specific problem. And now there's others who are doing this. There are services at Google, Amazon, Azure, and so forth, Intel's biggest customers, that are doing this for you. And on the system side, I wanted to mention just as a recent paper that came out from Berkeley, which I thought was very instructive. So the current state of AI, the current state of machine learning systems, the current algorithms being used, it is a highly unsatisfactory state of affairs. I feel like things are going to change. So when you're thinking about the space, try to look forward and don't assume that anything that's going on today is going to be there even a week or a year down the road. So some researchers at Berkeley tried to state the issues and challenges with AI and some research ideas. So these areas, so the trends, I'll just go through this briefly. So what are some of the system level issues with building an AI platform? So personalizing is really critical. We want to have models that are trained to the idiosyncrasies of the person, whether it's an accent in their voice for a voice recognition system, or whether they're driving in a country where there's lots of bad weather and the roads are not labeled. There's local statistics. There's also privacy of the person's data. Can you communicate this data that is very precious to the individual and private? Can you communicate it securely using some method like differential privacy or homomorphic encryption or whatever? This is one critical component to building these systems. Personalization also requires more compute because you essentially have to have a model per person in some sense. Other aspects that are very challenging, again, are the von Neumann computer in the brain idea, where you have to have exact computation with inexact elements. You want to have assurances that your AI systems are going to perform exactly, that they're not going to crash your car, that they're not going to let an intruder, a cyber threat, come into your system. You have to build systems that have some assurances that they're going to work robustly and reliably. That's another main challenge. And those arrows are to the research areas where they touch. So, for example, building a mission-critical AI requires being good at doing adversarial learning. Deep neural networks are very susceptible to adversarial examples. If you take an image of a dog and you add random white noise to it, potentially a convolutional neural net can label it as a spaceship. These kinds of things can really trip up these systems. If you're driving down some road and some bad person has put up some weird thing on a sign, your autonomous driving system might pick that up and crash. We have to solve these problems, and people are thinking very hard about how to make these algorithms robust. But again, these are some of the research avenues for, again, building things at the system level. I just encourage you to look at this paper. And we're at Intel. So what does Intel have to address these problems? This is the stack of things, and it's pretty cool. It's very fun for me because I have to wrap my head around all of these things as a neuroscientist. Neuroscientist is unfortunately not represented anywhere in there, so none of my skills are fungible. But at the bottommost layer, Intel is making processors, general purpose processors. It has FPGAs. FPGAs are pretty cool things. The fabric of an FPGA, it's a very fine-grained, distributed, reconfigurable fabric. The elements are actually multiply, adds, and lookups, so they're very neural networky. And the challenge is to configure these FPGAs to do neural network operations, and they are being exploited to do limited precision inference, for example, today, and potentially for other things in the future. We are building neural network processors as well, but there's a whole host of other technologies at the hardware level that are really critical for building systems. So memory, I mentioned, is very important for our processor, HBM2, HBM3, as well as for building a system, you have to have SSDs of various speeds and densities, and it has to be local, and it has to be remote and cached locally. You have to have interconnects that are very speedy. We have silicon photonics. That's the next generation of interconnects. Interconnects are really critical at the data center scale because if you're, for example, a Google or a Facebook or one of these large entities, you can split up operations across your data center much like the brain. The interconnects are 7 microseconds, and the inferences for deep learning are on the order of 10 milliseconds. So you can actually build a rack that just does computer vision, a rack that does just a speech, a rack that serves all your web pages, a rack that has in-memory data stores, and that's really enabled by the interconnects. So again, it's a critical piece of building an AI system. And on top of these things, I mentioned already some low-level libraries for doing linear algebra, deep learning primitives like convolution, as well as data flow graphs and other things. The framework layer, TensorFlows and whatnot, we optimize them for all the different kinds of hardware we have, and as well as the end solutions and experiences and the industry partners and customers that we work with. Some problems are open problems where we're working alongside our partners and customers to solve them. Some of them are fairly straightforward applications of existing technology, like the application of diabetic retinopathy I mentioned earlier. I think that was my last slide. Yeah, so that's pretty much it. So starting with von Neumann, computer in the brain, and this idea of listening to silicon, we're now in a good state where I'm looking around Intel and I'm coming up with a new team that's doing some new thing and thinking about how to listen to the silicon and try to apply it to my domain, as well as this paradigm shift in computation that we're very cognizant of at Intel, that processing is becoming more, computing is becoming more data processing. We're doing more learning and inference on data. And that's the end of my talk. I think I have some time for questions. Okay. Thank you.
Ask you, when you want to ask questions, let's queue up by these microphones. That way we don't have this left to right divide. And Amir was struggling with left and right anyway. So please, if you have a question, go to the microphone.
Ready?
Yeah, please, go ahead.
Okay. This is an excellent talk. On the other hand, could you give me your view about how the computer science education should be conducted in higher education institutions to develop people so that in future they can take on this type of projects?
So it's a great question. So it's very tricky because the current state of neural networks and deep learning and state-of-the-art in machine learning, basically all you need to know is calculus and the chain rule and some linear algebra. But if that's all you learn, you're going to be very unprepared for what's going to happen next. So, and this is a really unfortunate thing that academics are moving away from these institutions and going into places like Uber. Peter Dayan, one of my favorite neuroscientists, just joined Uber, which is like a tragedy. It's like I was so shocked. Well, my cousin is actually the CEO of Uber now, so I'll yell at him for doing that. But so I don't know how to answer your question, but I would just suggest that they learn a diverse set of things. They learn about interior point methods, how to take square roots of matrices, learn all these other things that are just, they've been swept under the rug because deep learning has been so successful. So I don't know how to answer this, but at one institution we work with closely, Berkeley and also MIT, people are, they're doing this. They're teaching graphical models, non-parametric Bayes. Those are the things that I actually learned about when I was a student. I thought deep learning was ridiculous for the first couple of years that I was like, this is never going to work, and this is really stupid. And my punishment was that I had to start a company to build these things.
But would you advocate the approach like you took going through the fintech world?
The fintech, would I advocate that?
Yeah.
Depends on who you were before and who you want to be after. I was studying string theory, so I didn't know anything about anything else. I was very focused on operator product expansions and probably had poor hygiene and didn't have any friends. So for me, it was very helpful. When I started in Wall Street, I didn't know what the Federal Reserve was. And this is why we have these crises, people like me. So that's a great question. I actually don't know how to answer that, but one of my relatives is very involved in CS education at an institution called code.org. He's doing it not at the higher education, but at the high school and less level on how to educate people in computer science. So I think that's a pretty effective strategy, just basic training in computer science. It's not all ML. It's lots of other things, building databases and being good at writing code. That makes them successful in the business, but potentially not in the research side. Everyone is doing convolutional neural nets now at CVPR. It's a tragedy.
Thank you.
You give interesting answers. Some of us know what Federal Reserve is. We have no idea why are we better off with it, so we would like to see it gone, but let's not go.
Okay, I don't have any opinions on that.
Okay. I spoke to Marvin Minsky, now deceased unfortunately, about 11, 12 years ago in Boston, and he was adamant that for general purpose AI, you need symbolic AI. Before the rise of deep learning, but you're aware, I'm sure, neural networks were popular, and then, hey, they can't do XOR, the weighted linear functions, and then they got unpopular and nobody funded them, and then in the 80s they got popular again. Now they're popular because of GPUs, not only, but and the nature of applications and so on and so forth. So your diagram of where we are, is it a trend? Is it the nature of applications? The kind of things that are amenable to this kind of image analysis, video analysis, and so forth. Are we anywhere closer to general AI with deep learning than we were with whatever was tried out before? Is there such a thing as general AI? Maybe not. I don't know. What are your thoughts, and how do you view trending versus fundamentally this is where AI is heading to?
Okay, that's a long question.
Sorry.
So the point was really critical about what you said about Marvin Minsky, and what's happened since the birth of AI is that there's been trends and fads that have come and gone. So what you just mentioned about doing symbolic computation was there from the very beginning. There was Skinner and there was Chomsky. Skinner was someone who did correlations. Chomsky believed that grammar is inherent to how your brain is structured. And you're seeing today more of Skinner than Chomsky, and invariably this is going to change. And we're going to have better incorporation of these other ideas, probabilistic grammars, and so forth, and to be able to solve problems. You have a problem like machine translation that's been marked as solved by Google and others, that you have input language, output language, and you have large corpora of each, so you can actually brute force this mapping. But if you look at the failures of these models on some adversarial examples, it's really clear that the model doesn't understand language. So how is that going to happen? It's an open problem. but it's going to mean that we move towards this Chomsky-esque world. And it's going to move back and forth. There's an excellent discussion about this topic by Peter Norvig on his webpage. I would highly recommend. He gives a pretty balanced view of these things. And you have people like Chris Manning, who is a top machine learning researcher at Stanford. And recently he gave a talk where he showed his own results in machine learning and translation. He had a number, better than the last thing. And next to it, he had like an unhappy face. And people ask him, why are you unhappy about this best result? It's like, well, it's really clear to me that the system, I don't know how this thing works. I don't think it has a really good understanding of language. I'm a linguist. I know that it doesn't incorporate all these ideas, that it's not going to be this future that Jeff Dean envisions, that you're just going to just move and then things are going to get better. It's going to stop at some point. So people are thinking about this hard, very hard. I don't know about general AI, but the hard problems of AI seem to be still hard. That some of the best robotic researchers in this field, they're in DARPA competitions. They're incredible engineers and brilliant people, but they can't get a robot to get out of a car and unlock a door. That's a very difficult task. The task of picking up a cup from a table is potentially more difficult than doing AlphaGo. That said, I'm very optimistic about the near-term future and the far-term future, and I think what's happening today is actually great. We're having innovation in algorithms, compute, data, that's actually helping people, and we're getting more money, and it's just a virtuous cycle that we want to keep and nurture and propagate. It's my responsibility, and you in the room as well. And then potentially we'll get to these questions in the future.
So one of the challenges of designing hardware is, of course, it's hardware.
Yeah.
And so you have to make a lot of decisions.
I'll never do it again.
And make it stick. So one of the issues that people are considering is to make efficient hardware is you might choose smaller numbers for weights, and then there's a lot of different choices. So have you found in designing this that you can have some flexibility, whether you can use all these many multipliers, so you can use 4-bit numbers, or you can use 64-bit floating point numbers, and
this is a great
your cake and eat it too.
Great question. So Jan actually touched on this idea of going from 32 bits to single bits. There is a trade-off between individual weights and their precision and the total set of bits that you have to use for your model. So there has been a trend that has been pretty consistent, going to smaller weights, smaller activations, smaller bit widths, single bits even, and it's been very successful. There are some things that are obstacles in this trend, that stochastic gradient descent, the algorithm that people use to train deep learning models, requires very large accumulations. So that accumulation has to potentially happen at a high precision. So in these smaller bit width models it's a very successful trend. There has to be something that's around that's a high precision thing, or it's still multiplication rather than XOR and so forth. But one of the things to keep in mind is that there is this trend to go from 32 bits to single bits, and perhaps when we reach single bits, it's a natural convergence to a limit. It's actually a fundamentally different kind of computation that's happening in single bits. And there's a very rich history in neuroscience and statistical thermodynamics, where people worked with Ising models and Potts models in the 80s and 70s, where they had really remarkable results. I feel like there's two things that will happen. You'll come to single bits, you'll put them into things like FPGAs, but also potentially we'll have this really cool set of discoveries, and single bit computation is not really just this convergence, but it's a new form of computation. It relates to, there's papers published on this if you want to look them up. Binary neural networks, Hopfield nets, single bit networks, there's relationships between that and solving random KSAT. This is a very intractable problem that relates to belief propagation and graphical models. So hopefully we'll have both. We'll have single bit things that are very efficient for edge devices, as well as discovering a new kind of computation.
What size does Nervana use for numbers?
We're using a various set of things, but We use the basic idea is simple. We use low precision multiplies, high precision accumulates. This is the kind of the trend that you're seeing, whether you go up or down.
And if I might be allowed, one more thing is, have you explored neuromorphic?
Have I explored neuromorphic? Yes, for 1 year I was at Qualcomm building neuromorphic processors.
So, if it's a very quick questions because we're running out of time, so.
Okay. So you replace your DDR with HBM, right?
Yes.
So what about the processor ASIC? Is that a regular SoC design or it's a 3D IC design, except of your HBM?
What is the actual technology? It's TSMC CoWoS. So it's
2.5D, I believe, right?
You
Whatever.
know more than I do. It's all these numbers.
And what's the speed of your processor?
It's on the. So our processor technology is. Since it's new technology, we want to make it somewhat like the GPU. Mm-hmm. So it's on the same order of.
So it will be competitive then.
1 gigahertz or around there.
Okay.
More.
Thank you.
Thank you very much.
All right. Thank you.
Thank you very much. Appreciate it.